All right, so now I'm going to show how you can think of the midpoint rule as a variational integrator. Okay, so you're given a Hamiltonian H, which is mapped from the cotangent bundle T star Q to the rails. All right, and then you have the midpoint rule. There's a map. Let's call that FH, which is a map from Q0, P0 to Q1, P1. And if you let, let's call it Zi be Qi, Pi, then the midpoint rule can be written as follows. So Zi minus Z0 over H is equal to the Hamiltonian vector field XH, okay, Z1 plus Z0 over 2. Okay, all right, so this is the midpoint rule. And you can write this in component form, right? So in components, this is just Q1 minus Q0 over H is dH dP, right? Q1 plus Q0 over 2, P1 plus P0 over 2, and then P1 minus P0 over H is equal to minus dH dQ of Q1 plus Q0 over 2, P1 minus, or P1 plus P0 over 2. Okay. All right. So how can we think of this as a variational integrator? Okay. So let's say that the Hamiltonian is regular, then there's a corresponding Lagrangian to that, right? If H is regular, then there is a corresponding Lagrangian. Let's call that L. Okay, and you can consider the following discrete Lagrangian. Okay, so I'm going to call this LD1/2. And it's called LD1/2 because if you recall, we discussed this family of discrete Lagrangians, LD alpha, and this is the case where alpha is equal to 1/2. Okay, so LD1/2 is Q0, Q1, and H. This is just defined as the H times the Lagrangian evaluated at the midpoint, Q1 plus Q0 over 2, and then the sort of finite difference approximation at velocity Q1 minus Q0 over H. Okay. All right, so let's see, what that gives you. Okay, so that tells you that P0 is equal to minus d Q0 LD1/2 Q0 Q1 H, right? And it's also P1 is equal to d Q1 LD1/2 Q0 Q1 H. And let's see what they correspond to. Okay, so this is minus H over 2 dL dQ, all right, evaluated at the appropriate point. Okay, so the the minus sign comes to the minus sign here. The 1/2 comes to the fact that you're differentiating the Q with respect to Q0. So q is q1 plus q0 over 2. If you differentiate it with respect to q0, you get a factor of half, right? Which is where that comes from. Okay, q1 plus q0 over 2, q1 minus q0 over h. And then now there's a term which involves the derivative with respect to the velocity, all right? Plus dl dq dot q1, okay, plus q0 over 2, q1 minus q0 over h. All right, then you have to differentiate q1 minus q0 over h with respect to q0, and that gives you a minus sign and a 1 over h factor. Okay, so the minus sign and the 1 over h factor cancels out the minus sign here, and it cancels out the h here, and that's why you get this term. Okay, so anyway, so you can do something similar now with this other term. This gives you h over 2 dl dq q1 plus q0 over 2 q1 minus q0 over h plus dl dq dot, okay, q1 plus q0 over 2 q1 minus q0 over h. All right, so that's what you get. And then what you can do is that you can subtract these two terms from each other, right? And then you can add them, and you get two different things. So let's see what you get. Okay, so you get on the one hand p1 minus p0. Okay, so if I take this and you subtract p0 and you divide it by h, right, you get dl dq q1 plus q0 over 2 q1 minus q0 over h. And on the other hand, if you take you add the two of them and you average them, p1 plus p0 over 2 gives you dl dq dot q1 plus q0 over 2 q1 minus q0 over h. Okay, so the second equation is a statement about the fiber derivative, right? So the second one basically says that okay, q1 plus q0 over 2 p1 plus p0 over 2 is equal to the discrete fiber derivative, sorry, not continuous fiber derivative, right, because it's this dl dq dot, okay, applied to q1 plus q0 over 2 q1 minus q0 over h. All right, and of course you know that continuous fiber derivative is exactly what relates the Lagrangian flow with the Hamiltonian flow. Okay, all right, so what that is telling you then is that evaluating dl dq, it's like on these things, right, is equivalent to evaluating d minus dh dq with respect to these variables. Okay, because you know, or you can check that dl dq, right, which depends on things in tq composed with fl is equal to minus dh dq. Okay, so this is one observation which comes from continuous, the relationship between continuous Lagrangian and Hamiltonian mechanics. All right, and so this equation, if you will, just comes from, this equation just comes from this thing together with this observation. Yeah. Okay. All right. So that's one part. Yes. Okay. So yeah. So this is related. This is equivalent to this because of this observation and this condition here. Okay. And then the other part is that So the other part has to do with how the inverse, if you will, it's like of the Legendre transform is related to the to this term here. Okay, so so how should I best say this? So it has to do with the fact that FL, as you know, is a map from TQ to T star Q. All right, and then there is sort of a analogous thing, which is the fiber derivative of the Hamiltonian, which is a map from T star Q back to TQ, and it has the form QP gets mapped to Q, comma, DH dP. Okay. All right, and if you think of the usual Hamiltonian, it's like which is 1/2 kinetic energy, more or less. It's like you know, 1/2. It's like sort of this sort of PM inverse P term. It's like which is the kinetic energy term, right? Then this corresponds to basically like M inverse P, which is of course the velocity, right, in the usual way. So this, okay, so anyway, so the point, if you will, is that FL and FH are inverses of each other. So if you take FL and you compose it with FH, you get the identity on TQ. All right, so what that means is that if I apply the discrete Hamiltonian map on both sides of this, okay, then I end up recovering this equation. Okay, so let's see that. So I'm going to just block this off, right? So this is the stuff coming from the midpoint rule. Okay, and I'm going to see how this observation gives me the second thing. All right, so you know this is equal to this, right? So you can apply FH to both sides. Okay, so FH of Q1 plus Q0 over 2, P1 plus P0 over 2, right, is equal to FH composed with FL, Q1 plus Q0 over 2, Q1 minus Q0 over H. Okay, but FH, if you will, is DH dP evaluated on this thing. Well, technically it is Q1 plus Q0 over 2 DH dP, Q1 plus Q0 over 2, P1 plus P0 over 2, right? But this thing, of course, is the identity. So this is just Q1 plus Q0 over 2, Q1 minus Q0 over H. Right, so the first terms, of course, clearly agree with each other. So you equate the second term, says that Q1 minus Q0 over H is DH dP evaluated on this, which is exactly this statement here. Okay, so that shows again that the you know, this midpoint discrete Lagrangian, which corresponds to this alpha family of discrete Lagrangians, right, gives you a map which is equivalent to the usual midpoint rule method. Okay. So let me just stop here for now.